For decades, the world of neuroscience has been locked in on a single culprit for Alzheimer's disease, these sticky plaques made of amyloid beta protein that build up outside our brain cells. And the logic seemed pretty simple, right? Get rid of the plaques and you save the brain. But a whole series of really surprising clinical trial results has created this huge paradox, forcing us to ask a really, really tough question.
And this is it. This is the question that's turning a 30-year-old hypothesis on its head. I mean, we now have drugs that can actually remove amyloid plaques from the brain. And let's be clear, that's a massive scientific win. But here's the problem. For so many patients, the cognitive decline just keeps going, almost like nothing changed. This huge disconnect is telling us that the plaques, well, they're not the whole story. In fact, they might not even be the main story.
So in this explainer, we're going to dig into that amyloid anomaly. We'll look at a much deeper problem happening inside our cells, uncover some unseen culprits, and figure out why good proteins go bad. Then we'll connect that molecular chaos to cognition, and finally look at a whole new frontier for treatment. All right, first things first, let's unpack the idea that has really dominated this field for an entire generation, the amyloid cascade hypothesis. So back in the 90s, the theory was pretty straightforward. Misfolded amyloid beta proteins clump together outside of neurons, they form these plaques. And those plaques were thought to set off this whole toxic chain of events, eventually killing the cell and wiping out memories. It made sense, and it drove billions of dollars into research. But now, fast forward to the 2020s, and the clinical data is forcing a major rethink. It seems the villain we were all so sure about might just be one piece of a much, much bigger puzzle. So if the plaques aren't the main driver, what is? Well, the evidence is starting to point away from the space between ourselves and deep, deep inside the machinery within our neurons.
This quote from Dr. Stephen Fried, Johns Hopkins, just nails it. The plaques are just the tip of the iceberg. It perfectly captures this huge shift in thinking. The visible plaques that we've been focused on, they might just be a late-stage symptom of a much wider, more fundamental crisis, a total breakdown of the cell's quality control system.
And that system has a name. Proteostasis. Honestly, the best way to think about it is as the cell's entire operations management. It's the whole shebang. It makes sure that the tens of thousands of different proteins inside every single neuron are built right, folded into their exact 3D shape, shipped to the right place, and then, crucially, taken out with the trash when they get old or damaged. As we age, and especially in neurodegeneration, this entire system just starts to fall apart. So this really clarifies the massive shift in perspective. The old amyloid hypothesis, it was all about insoluble, clumpy aggregates of just a couple of proteins happening outside the cell. But this new proteostasis model, it's focused on a proteome-wide collapse inside the cell involving hundreds of different soluble, misfolded proteins that are causing chaos long before they ever form big clumps. So you might be asking, okay, where's the evidence for this huge proteome-wide collapse? Well, it comes from some absolutely incredible work in structural proteomics, looking right into the brain's memory center, the hippocampus. Using a new technique that can basically map the shapes of proteins on a massive scale, researchers compared the brains of aged subjects with normal cognition to those with memory problems. And what they found was stunning. There were 214 distinct proteins that had misfolded only in the memory-impaired group. And these were not amyloid or tau. They called them cognition-associated structural changes, or CASCs for short. And the scale of this damage is just immense. We're talking about proteins that are absolutely critical for a neuron's most basic jobs, things like communication at the synapse, building new proteins, and even generating energy. But here's the really cruel twist. Some of the proteins that are failing are the ones whose job it is to help other proteins fold correctly. So the quality control system itself is failing, which creates this vicious, self-perpetuating cycle of disaster inside the cell. This brings up a really fundamental question, though. Why are these specific 214 proteins so vulnerable? I mean, why them? Well, the answer seems to lie in their basic physical design. So it turns out many of these Cas proteins are what we call non-refoldable. Now, unlike simpler proteins that can kind of find their correct shape on their own, these guys are like complex, intricate pieces of machinery. They are totally dependent on the proteostasis network, especially other proteins called chaperones, to help them fold correctly right after they're made. They have zero ability to fix themselves if they get damaged or unfold later. So you can see how this becomes a one-way street to disaster.
A new, non-refoldable protein gets made, and with help, it folds perfectly. But as we get older, our proteostasis network gets weaker. So when that protein inevitably runs into some cellular stress and loses its shape, the support system that helped it fold in the first place just isn't there anymore. It gets stuck, what scientists call kinetically trapped, in a useless, misfolded shape, forever. It's now just a piece of molecular junk gumming up the works.
So how do we get from this molecular chaos, this protein garbage piling up inside a cell, to the devastating experience of memory loss? How do we connect those dots? Well, it's all about location. The hippocampus is the brain's headquarters for learning and memory. The neurons there are some of the most active in our entire body, constantly firing, constantly building new proteins to store our experiences. All that activity creates a ton of wear and tear, making the hippocampus basically ground zero for a proteostasis collapse. The system just gets completely overwhelmed. Now, here's something you might not expect. One of the earliest signs of cognitive decline isn't that brain circuits go quiet. It's that they actually become hyperactive. But this isn't good activity. It's a noisy, chaotic state called runaway excitation, where neurons are just firing uncontrollably, completely disrupting the delicate dance of memory formation. And this new research gives us a perfect molecular explanation for that chaos. Let's take just one of those 214 Cas proteins, a protein called gefferin. Its normal job is to act like a scaffold, holding the brain's main off switches, the inhibitory GABA receptors, in the right place at the synapse. So when gefferin misfolds, it can't do its job. The inhibitory synapses basically fall apart. And what happens? The brain loses its braking system. And that leads directly to the runaway excitation that scrambles memory. So understanding this deep systemic failure, it completely changes the game for how we approach treatment. We can finally stop focusing on just one symptom, the plaques, and start thinking about treating the real underlying disease, the collapse of the entire proteostasis network. This new playbook is all about reinforcement, not just removal. The goal is to develop therapies that can actually boost our body's own natural defenses. We're talking about drugs that could supercharge our chaperone proteins, helping them do a better job of refolding things. Or maybe therapies that activate the cell's garbage disposal systems, the proteasome and autophagy, to clear out all that accumulating junk. We could even use AI and proteomics to spot these network failures years before symptoms show up, opening the door for genuine prevention.
Which really leaves us with this powerful final thought. For 30 years, we've basically been acting like janitors, trying to clean up a huge mess after it's already been made. But this new proteostasis model suggests a totally different role, the role of an engineer. Maybe, just maybe, the key to protecting our memories isn't about desperately scrubbing away the damage, but about reinforcing the elegant, beautiful systems that were designed to prevent that damage from ever happening in the first place.